Okay, welcome back to McNab Chemistry. Today we're going to have a look at stereoisomerism. Okay, so stereoisomers are compounds which have the same structural formulae, but the bonds are arranged differently in space. Okay, and there are two types of stereoisomerism that we need to learn. They are EZ stereoisomerism, it's also known as geometrical isomerism or cis-trans isomerism, and optical isomerism. Okay, so today we're going to consider EZ stereoisomerism. Okay, so EZ stereoisomerism, as I've just said, it's also known as geometrical isomerism or cis-trans isomerism. Okay, and really when you're approaching this topic, there are just four key areas that you need to be aware of. Okay, so there are four areas of knowledge we need to fully understand this topic. Okay, first of all then, whenever you've got an organic molecule where you've got a carbon-carbon double bond present, there is restricted rotation in the molecule. Okay, so that's key to EZ stereoisomerism. Okay, so the presence of a carbon-carbon double bond results in restricted rotation in a molecule. Okay, so basically groups within the molecule can't rotate. Okay, point number two, E stands for entgegen, which is German for opposite, and Z stands for zusammen, which is German for together. Okay, so E is opposite and Z is together, or a good way of remembering it is Z is same, 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 Z, same. Okay, and then you also need to know about the Kahn-Ingold prelog, the CIP rules, which enable us to work out the priority groups on either side of the double bond. Okay, and this is an application of atomic number. Okay, this will all make sense in a minute. Okay, right, so note then, EZ stereoisomerism is not possible when there are two identical groups joined to the same carbon. Okay, so if I look at this molecule here, I can see that on that carbon there, I've got a hydrogen and a hydrogen. Okay, because those two groups are the same, then this molecule here cannot show EZ stereoisomerism. Okay, right, so the best way to understand this topic is actually just to look at some examples and work your way through. Okay, so let's have a look at this molecule here, meth, eth, pro, bute. It's bute-2-ene. Okay, my double bond is between the second and the third carbon. Okay, and then attached to this carbon here, I have a CH3 group and an H. Attached to that carbon, I have a CH3 group and an H. Okay, we're going to consider these two groups then. Okay, and we need to decide which of these two groups takes priority. Okay, so the way that we apply our CIP rules is we look. So I'm trying to decide whether this group or this group takes priority. Okay, so I look to see which atom that's attached to the carbon here. Okay, which one of these two has the highest atomic number. Okay, so in that case, the first atom that's attached to that carbon, that's a carbon, that's a hydrogen, that has a greater atomic number than that hydrogen, so that's my priority group on that side. Then on my right hand side of the double bond, this is my priority group because that carbon has a higher atomic number than that hydrogen. Okay, so we'll look at it again in a little bit more detail. Carbon-carbon double bond. Okay, look to the left, look to the right of the carbon-carbon double bond, decide which your priority group is, and if your priority groups are both on the top, then they're both on the same side, aren't they? Okay, so they're both on the top, they're on the same side, so it's Z. Okay, so there we go. Which of these two is my priority group? So I look, find my double bond, look to the left, which of these two is a priority group? That's a priority group because the carbon has a higher atomic number than the hydrogen. Look to the right, compare that group and that group, which is a priority group? Well, it's this one because that carbon has a higher atomic number than that hydrogen. Okay, so my priority groups are both lie above the double bond, they're both on the same side, so the stereoisomer is the Z stereoisomer. Okay, let's read through this carefully. Okay, so to work out which group that on the left hand side takes priority, apply the CIP rules. Right, CIP rule application then, ask yourself the question, which atom that is directly attached to the carbon on the left of the double bond has the higher atomic number? Okay, the answer is the C of the CH3. Okay, so therefore the CH3 group takes priority. Then look to the right of the double bond, which group takes priority? Okay, and then in this case the left and the right priority groups are on the same side, so therefore it is the Z isomer. Okay, just to recap then, I just like to look at the molecules with these. Okay, and so there's my double bond. Okay, and then on the left hand side of my carbon-carbon double bond, I've got this group and I've got this group. Okay, apply my CIP rules. I look at that carbon and I look at that hydrogen. That carbon's attached to that carbon, that hydrogen's attached to that carbon. So I'm comparing these two. Which of these two has got the highest atomic number? It's the carbon, so that is my priority group. Okay, on this side, I look to the right of my carbon-carbon double bond then. Which of these two is my priority group? Well, I'm comparing the atomic number of carbon compared to the atomic number of hydrogen. The carbon atomic number is greater, so that's my priority group. My two priority groups on the left and the right hand side of the carbon-carbon double bond are both on the top, they're both on the same side, so it's the Z stereoisomer. Okay, so the priority groups are both above the double bond, i.e. are on the same side, therefore we name this Z-but-2-ene. Okay, it's also known as the cis isomer of but-2-ene. Okay, so let's consider the geometrical isomers of 2-chloro-prop-1-enol. So it's got the double bond, the ene is an alcohol because it's an ol, and it's got a chloro in position 2. Okay, so it's this molecule here. Okay, so let's have a look at this one. We're trying to work out whether this is the E or the Z isomer of 2-chloro-prop-1-enol. Okay, so I find my double bond's there. I look to the left of the double bond, so I'm comparing this group and this group to decide which is the priority group. I apply my CIP rules, and the O has got a greater atomic number than the H, so that's my priority group on the left hand side. I then look to the right of the carbon-carbon double bond. The Cl has a higher atomic number than the carbon, so my priority group this time is the Cl. Okay, my priority groups on the left and the right are both on the top, they're both on the same side. Okay, so that is Z-2-chloro-prop-1-enol. Okay, so the two highest priority atoms are both on the same side above of the double bond. Okay, so therefore this is Z-2-chloro-prop-1-enol. Okay, let's have a look at the other isomer, the other stereoisomer. Okay, so I find my double bond, I look to the left, I'm comparing this group and this group, I apply my CIP rules. Okay, so oxygen has a higher atomic number than hydrogen. Okay, so that's my priority group on the left. Look to the right hand side of the carbon-carbon double bond. Okay, the chlorine has a higher atomic number than the carbon, so that's my priority group on the right hand side. So on this side my priority group was at the top, on this side my priority group was at the bottom, so my priority groups are opposite each other, so that is E-2-chloro-prop-1-enol. So in this geometrical isomer, the two highest priority atoms are on the opposite side of the double bond, i.e. one above and one below, so this is the E isomer. Okay, so finally, to make sure that we fully understand how to apply the CIP rules, consider which group would take priority if we had. Okay, so this is my molecule here. Okay, so I find my double bond, I look to the left, and I can see there that I've got a carbon attached to that carbon, and I've got a hydrogen there. So carbon has a higher atomic number, so carbon, this group here, is my left priority group. Then I look to the right of the carbon-carbon double bond, so I'm looking at the right, I'm comparing this group and this group, but I compare the atoms, don't I, that are attached to that carbon. So this carbon here is attached to that carbon, this carbon here is, well, they're the same atoms, so I need to then move to the next atom in the chain. Okay, well, this group at the bottom, my next atom in the chain is that carbon, and on that carbon my next atom in the chain is a hydrogen, so I'm comparing this carbon with this hydrogen. This carbon has a higher atomic number, so therefore this group takes priority. Okay, so I've just summarised it a little bit like this here. I've called these position 2, so there's my carbon-carbon double bond going this way. For both groups, a carbon is attached to that carbon. Okay, and then, so therefore, because they're the same, I have to go to the next atom on the chain. So that is then a hydrogen, and that is a carbon. That carbon there has a higher atomic number. Okay, so this is my right priority group. So right priority 1. Okay, and so we compare the number of, we compare the number 2 atoms. Carbon has a higher atomic number than hydrogen, therefore the CH2CH3 is the right priority group. Okay, let's have a little look if we had this as 2 groups to compare. Okay, I've got this group here with an OH group, and I've got this group here, CH2CH3 group. Okay, so that carbon and that carbon, they're both the same. So then I need to move to the next atom in the chain. That's an oxygen, and that is a carbon. Oxygen has a higher atomic number than carbon, therefore this group would take my priority. CH2OH would be my priority group because the oxygen there has a higher atomic number than the carbon there. Okay, I hope that's been helpful. Thank you for watching, and don't forget to like and subscribe and click on the bell notification to stay fully updated.